Welcome. If you're deep into your power plant certificate studies right now, you definitely know that the light-scored aircraft, or LSA category, well, it demands some pretty specialized knowledge.
Oh, absolutely. This isn't just, a small corner of aviation anymore. It's growing fast, and it's really defined by this relentless push for efficiency and some very specific rules.
Right. When you look under the cowl of an LSA, you're typically not finding those classic big-bore American engines we spend a lot of time on.
Exactly. You're often looking at engines that are super lightweight, very high power-to-weight ratio. Sometimes they're heavily modified car engines or these really cutting-edge European designs. They're all built to hit very strict weight and performance targets.
So for you, the AMT student, getting a handle on these differences, it's not just nice to know, it's essential.
Couldn't agree more.
So our goal today is to really break down the essential technical info. We're talking LSA engine requirements, digging into the key systems, especially ROTACs, which you see everywhere, and really nailing down those specific, sometimes unique maintenance steps.
Think of this as your roadmap, getting you fluent in the LSA power plant world.
Okay, let's start right at the foundation. For any AMT, you've got to know the rules, the hard limits that define what a light sport aircraft actually is.
Yeah, these limits basically drive every single engineering decision, especially when it comes to the engine, its weight, its power output.
The LSA rules, they sort of create this very specific box the aircraft has to fit into.
That's a good way to put it. It's a set of non-negotiable specs. And top of the list, unsurprisingly, is weight.
And those weight limits are really the big one dictating engine choices, aren't they?
They really are. For a land plane, the max takeoff weight, it cannot be more than 3,320 pounds. That's 600 kilograms.
Okay.
Now, if it's designed for water operations, you get a little bit more wiggle room, up to 4,430 pounds or 650 kilos.
Doesn't sound like a huge difference, that 110 pounds.
You'd think so, but when you're optimizing like crazy for efficiency, every single ounce you save on that engine, maybe through design or materials, it translates directly into useful load, payload, passengers, fuel.
Yeah.
It matters a lot.
Got it. And it's not just weight. Speed limits come into play too, right?
Yeah.
Affecting the power plant.
Correct. The max speed in level flight, that's V sub H, using max continuous power, it's capped at 120 knots calibrated airspeed, CAS.
120 knots CAS? And for gliders.
Same limit for the never exceed speed, VNE, on an LSA glider, also 120 knots CAS. So, these limits encourage sleek designs, but they also mean you can't just bolt on an infinitely powerful engine. It has to fit the whole package.
You should probably also touch on stall speed, VS1. Seems like an airframe thing, but I guess it connects back to the engine weight and prop.
It absolutely does. Max stall speed without flaps or other lift devices can't be more than 45 knots CAS.
That's quite slow.
It is. And hitting that often demands a really lightweight airframe, which again circles right back to needing a lightweight engine. Plus, other rules apply if it's powered. Single engine only has to be reciprocating.
Okay.
Max 2 seats, including the pilot, and the prop, it has to be either fixed pitch or ground adjustable. No in-flight adjustment allowed under LSA rules.
Okay, that sets the stage. Now, engine reliability. This is interesting because a lot of popular LSA engines, like the Rotax models, they aren't formally FAA certificated under Part 33 like a Lycoming or Continental might be. So how do we know they're reliable?
That's a really key distinction for LSA. Reliability isn't necessarily proven through that FAA type certificate process. Instead, it's basically ensured by the manufacturer through really exhaustive design, research, testing.
So the onus is on them.
Right. And for engines used in factory-built special LSAs or SLSAs, they typically have to comply with these very rigorous consensus standards. Usually it's the American Society for Testing and Materials, ASTM standards.
A lot of ASTM.
These standards cover the whole life cycle design, testing protocols, manufacturing, quality control. It's a different path, but it holds the manufacturers to a high, verifiable standard.
It's like a performance standard, proving it works reliably in flight under different conditions rather than just ticking boxes on a form.
Precisely. They have to show it works across different flight attitudes, temperatures, altitudes. It's quite thorough.
Let's talk TBO time between overhaul. The source material mentioned, it varies a lot, especially based on how the engine's operated. The Rotax 914 was a good example.
Yeah, TBO is definitely not one size fits all here. It heavily depends on usage, things like engine temps, how often you're running at high power settings. For the Rotax 914F or UL, the baseline TBO is 1,000 hours or 10 years, whichever comes first.
Okay, 1,000 hours or 10 years.
But, and this is a crucial point for you as an AMT student, manufacturers often provide ways to extend that.
Oh, Like through service bulletins.
Exactly. For the 914, if you meticulously follow Service Bulletin SB 914027, which involves specific inspections and replacing certain parts, you can potentially push that TBO out to 1,200 hours or 12 years.
Wow, okay. That's significant.
It really is, and it highlights why staying absolutely current with the manufacturer's service instructions, not just FAA ADs, is so critical for LSA work. Missing a bulletin could mean you're recommending a costly overhaul way too early.
Good point. All right, speaking of doing the work, who's actually authorized to maintain these LSA engines and sign them off? For an AMT student, getting that Powerplant certificate is the goal.
Absolutely. Holding a power plant or the full AMP certificate basically lets you do almost any maintenance and inspection needed, as long as you follow all the rules, regulations, manufacturer specs, service bulletins, the works. That's your main pathway.
But LSA also introduced a couple of other roles, the non-certificated ones, that sometimes cause confusion out in the field.
They definitely do. First, the simplest one, the sport pilot. If they own or operate the LSA, they can perform preventive maintenance.
Okay, what does that cover?
Think really simple stuff listed in Part 43, Section 43.3G, like changing the oil, cleaning spark plugs, changing a tire. It's pretty limited. They definitely can't do major repairs or the required annual condition inspection.
Right. Then there's the more specialized role,
Yeah.
the repairman certificate for light sport aircraft.
Yeah.
That needs specific training.
Yeah, it does. First, there are baseline requirements. Going to be 18, proficient in English, show you have the skills for safe operation, and be a U.S. citizen or permanent resident. And crucially, this certificate is tied to a specific class of LSA, like airplane, weight shift control, etc.
And there are two different ratings under that certificate, inspection and maintenance. Why the big difference in required training hours?
It comes down to what they're allowed to do, their authority. The inspection rating just needs the baseline requirements plus a 16-hour FAA-accepted training course. Pretty short.
16 hours. What can they do?
Their privilege is narrow. They can only perform the annual condition inspection and only on an experimental LSA and ELSA that they personally own or operate. They can't do maintenance beyond preventive tasks. They're basically just inspectors for their own ELSA.
Okay, but the maintenance rating sounds much more involved. Closer to what an AMT does.
Much closer. Same baseline requirements, but way more training. For the airplane class rating, it's a minimum of 120 hours of instruction.
120 hours.
Yeah. For weight shift or powered parachute, it's 104 hours. That higher number, especially the 120 for airplanes, reflects the need for skills across the whole aircraft and engine spectrum for maintenance and repair.
And their sign-off authority is much broader, too.
Much broader. A repairman with the maintenance rating can approve and return an LSA to service after doing maintenance or inspections. That includes the annual condition inspection and the 100-hour inspections needed for aircraft used for hire under Part 91.
That's a big responsibility.
Huge. And the regs specifically say they must follow the manufacturer's instructions. And here's another key point. If they haven't done a particular task before, they have to demonstrate they can do it right under the direct supervision of a certificated AMP or another experienced LSA repairman.
That really drives home the point in LSA. The manufacturer's manual is king. Okay, let's pivot now. Let's talk about the engines that really kicked off the ultralight and LSA movements. The two-stroke Rotax line. The 447, the 503, the 582. These things are legendary for getting maximum power out of minimum weight.
They really are little powerhouses. Engineering marvels of efficiency for their time. They all share that inline cylinder setup using the two-stroke cycle, piston-ported. That narrow inline design, it gives them a really small frontal area, which is great for streamlining the aircraft, reducing drag.
And the cooling systems varied across the line, right? Showing sort of different levels of complexity.
That's right. The smaller ones, the 447 and the 503, they were mostly air-cooled, and you could get them in two main air cooling flavors.
Okay.
First was free air cooling, basically just using the airflow from the plane moving forward, and the prop wash. Simple, but maybe not great on the ground.
Right.
The other option was fan cooling. This used a dedicated fan, driven off the crankshaft with a V-belt. It provided a constant airflow over the cylinders, much more reliable, especially at low speeds or during ground runs.
But the 582, that one stepped up to liquid cooling, didn't it?
Yeah.
To handle more power, more heat.
Exactly. The 582 uses liquid cooling for both the cylinders and the heads. It has an integrated water pump built right in. The really neat part is the detailed two-circuit cooling setup.
How does that work?
Well, the pump pushes coolant through the cylinder jackets and the head passages. That hot coolant then goes out to a radiator. It's a closed circuit system, but you need to manage the expansion of the coolant as it heats up.
Ah, and that's where the expansion tank and the special cap come in.
Precisely. The expansion tank handles the volume change. The pressure cap is key. It has an excess pressure valve. When the coolant gets hot and expands, the pressure builds, the valve opens, and excess coolant vents through a hose into a transparent overflow bottle. That bottle's just open to the atmosphere.
Okay.
Then, when the engine cools down, the coolant contracts, creates a vacuum in the system, and a return valve in that same cap opens, sucking the coolant back in from the overflow bottle. Keeps the system full and sealed. Pretty clever. Ensures stable temps.
Moving to lubrication. This is where two-strokes are really different from the four-stroke engines most AMT students are used to.
Yeah.
Two main ways they do it.
Yeah, very different philosophies. The most basic, often seen on the 447 and maybe some 503s, is pre-mixed fuel. You literally mix the gasoline and the special two-stroke oil together in the fuel tank.
What's the typical ratio?
Usually 1.50. So for every 50 parts of gasoline, you add 1 part oil. That's 2% oil. Simple concept, but man, you have got to get that mix right every single time. Too little oil, you seize the engine. Too much, you foul plugs and make smoke.
High stakes for just mixing fuel.
Mm-hmm.
But the later 503 DCDI and the 582 DCDI, they used oil injection, right? Much more sophisticated.
Huge step up. Oil injection is way more efficient and cleaner. You have a separate oil tank. Then there's a small crankshaft-driven piston pump that precisely meters the oil.
Meters at where?
It injects the exact amount of oil needed directly into the intake stream, usually through little diffuser jets right before the carburetors. It varies the amount based on engine RPM and throttle position.
So the carburetors, they only ever see pure gasoline.
That's the beauty of it, pure gas in the carbs. The oil pump has a lever connected by a cable to the throttle linkage. You open the throttle, the pump delivers more oil to match the increased fuel flow. Takes all the guesswork and messy mixing out of the equation.
For students working on those older premix systems, though, getting that fuel-oil mixing procedure down pat is absolutely critical for safety. More than just the ratio, right? Cleanliness and static.
Oh yeah, safety first, always. You absolutely must use a clean, approved metal container. Know its exact volume. The trick is to predilute the oil first. Pour the measured oil into the can, add just a small amount of fuel, swirl it around, get it nicely mixed.
Get it homogenized before adding the rest.
Exactly. Then add the rest of the gasoline and pour it all through a fine mesh screen or filter funnel. Keep contaminants and water out.
And that serious warning about static electricity during fueling. That's no joke.
Cannot emphasize this enough. You must use only metal containers, and you must properly ground the aircraft according to specs before and during refueling. Static discharge is a massive fire hazard with gasoline, especially these volatile mixtures. Non-negotiable, every single time.
Okay, let's talk electrons. The ignition system on these Rotax two-strokes is famous for being independent, right?
That independence is a real Rotax hallmark. The 503 and 582 have dual ignition built-in redundancy, which is great. The 447 is single ignition. But they all use this breakerless magnetocapacitor discharge ignition, or CDI.
And the key thing for an AMT to know.
The entire ignition system generates its own power. It needs absolutely zero external battery power to run.
Meaning, if the aircraft battery goes flat mid-flight,
The engine keeps running, no problem. There are dedicated charging coils built onto the generator stator that power the ignition unit directly. External triggers handle the timing, capacitors store the charge, then zap. High voltage spark. It's elegant, robust, and basically maintenance-free from a power supply perspective.
though it can still power other things, right? Lights, radio.
Oh, sure. They usually have an integrated AC generator, maybe 12 volts, 170 watts or so. And you can get an optional external rectifier regulator unit to convert that AC to DC for charging a battery and running basic accessories. But again, the ignition itself doesn't care if that system is working or not.
All right. Let's move into the more modern LSA power plants.
Yeah.
The four-stroke Rotax 912 and 914 series. These are kind of the benchmark engines in the category now, right? Four-cylinder, horizontally opposed, known for being light, reliable, pretty smooth.
Definitely the workhorses.
Yeah.
The 912 and the turbocharged 914 really brought four-stroke reliability down to LSA-friendly weights. And their cooling system is, well, it's pretty unique. A clever compromise.
That's the hybrid system you mentioned. Liquid cooling for the heads, but air cooling for the cylinder barrels.
Exactly that. The cylinder heads, that's where combustion heat is most intense, most critical to control. They get liquid cooling. Closed circuit, expansion tank, radiator, the whole setup. But the cylinder barrels, they rely just on a ram air cooling from the airflow over the engine.
By the split.
It gives you the precise thermal control you need for the heads, especially on the Turbo 914, but it saves the weight and complexity of having full liquid jackets around the cylinders, extra pumps, more coolant, uses natural airflow where it can. Smart design.
Okay, let's get into the fuel system. This is where things start to get a bit more complex, especially with the 914 having that turbocharger.
Yeah, the fuel system has to be pretty robust to handle boost pressure. It usually starts with two electric fuel pumps connected in series. Redundancy again.
Always good.
Pumps pull fuel from the tank through a pre-filter. After the pumps, the fuel goes through a fuel pressure control unit and then to the two carburetors.
What's the specific job of that pressure control unit when you've got forced induction involved?
It's absolutely critical. Its job is to make sure the fuel pressure going to the carburetors is always kept at a specific pressure above whatever the air pressure is inside the airbox.
Above the boost pressure.
Exactly. Typically, it maintains fuel pressure about 0.25 bar, or roughly 3.6 psi, higher than the airbox pressure. Think about it, if the fuel pressure was just constant and the boost pressure in the airbox went up, that higher air pressure could actually stop fuel from flowing out of the carb jacks or lean the mixture way out.
Ah, right. So it needs that positive differential.
Precisely. This differential pressure control ensures the carbs get the right amount of fuel regardless of altitude or how much boost the turbo is making.
And managing excess fuel is important too. The return line.
Yes. Any fuel the carbs don't need gets sent back to the tank via a return line. And here's a maintenance point. You, as the AMT, need to know that return line cannot have any resistance. No kinks, no blockages. Any restriction will mess up the pressure regulator, probably make the carbs run rich or even overflow, and make sure the check valves near the pumps are working right too.
Got it. Lubrication system, also a step up from a simple wet sump, right?
Definitely. It's a dry sump force lubrication system, more complex, but it guarantees consistent oil delivery no matter what attitude the aircraft is in, important for aerobatics or unusual attitudes.
How does it work?
It uses a main oil pump, which has an integrated pressure regulator, plus an additional suction pump. Both are driven off the camshaft. The main pump draws oil from a separate external oil tank, pushes it through an oil cooler, then an oil filter, and then delivers it to all the bearings and lubrication points.
And the suction pump, what's its job?
Its job is to constantly scavenge oil that collects in the bottom of the crankcase, mostly from blow-by gases getting past the rings. That suction pump, or sometimes just the crankcase pressure itself, forces that collected oil back up into the external oil tank.
Keeping the crankcase relatively dry.
Exactly. There's also a separate oil line specifically to lubricate the turbocharger bearings on the 914. And importantly, the whole oil circuit is vented through a specific opening in the oil tank to prevent pressure buildup.
Okay, now the heart of the 914, that turbocharger, and its electronic brain.
Right. Standard turbo principle. Exhaust gas spins a turbine, which spins a compressor, which crams more air into the engine's airbox. This boost lets the engine maintain sea level power much higher up, but you have to control that boost very carefully.
And that control comes from the wastegate.
Yeah.
Which is electronically controlled.
Correct. The wastegate is like a bypass valve for the exhaust gas. By opening it more or less, you control how much exhaust actually hits the turbine, which regulates the turbo's speed and thus the boost pressure. The brain is the turbo control unit, or TCU.
What does the TCU look at?
It takes input from several sensors, but the main one is the throttle position sensor, usually mounted on one of the carburetors.
So throttle position tells the TCU how much boost to make.
Basically, yes. It sends a signal, typically 0% at idle, up to 115% at full power. And here's a really critical piece of info for maintainers and pilots. You need to be aware of the operating range between about 108 and 110% throttle.
What's special about that narrow window?
In that small range, the commanded boost pressure rises very, very rapidly. If a pilot moves the throttle really slowly or hesitantly right in that zone, the system can sometimes hunt or fluctuate. Pilots might call it surging.
Okay.
So as an AMT, if you hear reports of surging around full power, it could point to a wastegate issue, maybe a TCU calibration problem, or sometimes just the pilot needing smoother throttle technique through that specific range. Movement there should be deliberate.
And the TCU also acts like a safety system.
Absolutely. It provides really robust engine protection. If certain limits are exceeded, like engine overspeed, or if the intake air temperature gets too high, risking detonation, the TCU will automatically reduce the boost pressure to protect the engine from damage.
Smart. And there are warning lights tied to this system.
Yeah.
Vital for diagnostics.
Yep, two main ones. A red boost lamp and an orange caution lamp. They should both flash on briefly when you power up the system, just as a self-test.
What does a steady red light mean?
Steady red boost lamp means the actual boost pressure is exceeding the allowable limit. That points to a problem. Maybe the wastegate is stuck closed, or there's a mechanical issue with the turbo control. Needs investigation.
But the really critical one is if that red light starts blinking.
That's the big one. A blinking red boost lamp means the engine has been run at full throttle over that 110% power setting for longer than the permitted time limit, which is usually 5 minutes.
5 minutes max at full power.
Right. Exceeding that means potential thermal and mechanical overstress on the engine components. If a pilot reports that blinking light, you, as the AMT, absolutely need to check the engine log, potentially perform specific inspections looking for signs of damage because that engine was pushed beyond its continuous operating limits.
Okay, good to know. Now, Rotax dominates, but they aren't the only players. Let's look at some other opposed LSA engines, the HKS 700T.
Ah, yes, the HKS. It's a neat little engine, only 2 cylinders, 4-stroke, but it packs a punch because it's turbocharged and intercooled. And it uses electronic fuel injection, EFI.
Intercooled EFI on a 2-cylinder. Sounds complex.
It is relatively complex, requires specific knowledge. It's incredibly light, though, like 126 pounds. But that complexity and high specific output are reflected in its TBO, which is only 500 hours.
500 hours. Okay. Then there are the Jabiru engines, the 2200 4-cylinder and 3300 6-cylinder.
Yeah.
Very popular, especially in kits and experimentals. What's their main design difference compared to Rotax?
The absolute key differentiator for Jabiru is direct crankshaft drive. There's no reduction gearbox between the engine and the propeller.
Prop bolts straight onto the crank flange.
Exactly. That immediately saves a lot of weight, reduces complexity, and eliminates maintenance items associated with gearboxes. No gearbox friction checks, no separate gearbox oil. It's a simpler, lighter philosophy.
How do they build them to keep the weight down but handle the stress?
They use a lot of machine components instead of castings. Things like the crankcase halves, the cylinder heads, even the crankshafts are often machined from solid billet material, gives them strength. The cylinders are machined from tough 4140 chromoly steel, and the pistons run directly in those steel bores.
Interesting. And their cooling approach is different, too, for an air-cooled engine.
Very different from, say, a Lycoming. Instead of relying on tight-fitting metal baffles and big plenum chambers to force air through the fins, Jabiru developed these specific ram air cooling ducts, usually made of composite.
Ducts instead of baffles.
Right. These ducts are shaped to efficiently capture prop wash and direct it precisely over the cylinder barrels and heads. It works well, eliminates the hassle of maintaining traditional baffles, and generally make engine access a bit easier.
They seem to engineer for simplicity elsewhere, too. Ignition, valves.
They do. The ignition is fully redundant, electronic, and self-generating like the Rotax. But a key feature is that the ignition timing is fixed. No adjustments needed, ever. They use common automotive-style spark plugs and dual distributors. And another big plus, they use hydraulic valve lifters.
Ah, so no manual valve lash adjustments needed.
Correct. The hydraulic lifters automatically maintain zero valve clearance, which significantly cuts down on routine maintenance compared to engines with solid lifters that need regular checks and adjustments.
Okay, finally in this section, we have to talk about the modified engines. Those based on automotive cores like VW and Corvair. Super popular in the experimental LSA world. Let's start with the Aeromax 100 IFB.
Right, the Aeromax is based on the old 6-cylinder, air-cooled GM Corvair engine core, known for being smooth, direct drive. The absolute key modification they make is adding their integral front bearing, or IFB.
Why is that IFB so vital? A car doesn't need that.
Because a propeller puts completely different loads on a crankshaft than driving a car's transmission. You get huge dynamic loads, bending forces, and significant thrust loads that a car engine just never sees. That IFB and its special housing are designed specifically to support the nose of the crank and handle those aircraft-specific stresses, preventing crank failure.
Makes sense. Any other odds?
Yeah, the crankshaft itself is usually extended, ground true, and then nitrided. That's a heat chemical treatment that dramatically hardens the surface, making it much more resistant to wear and fatigue, and they emphasize that every remanufactured engine gets a thorough inspection and a mandatory 2-hour test run before it ships.
And the RivMaster R2300, based on the VW bug engine, right?
Yep, the 4-cylinder VW Beetle engine core. RevMaster has been converting these for aircraft use for decades. One unique feature for an engine in this horsepower class is that the R2300 is often set up for an oil-controlled constant speed propeller.
Constant speed prop on a VW conversion. That's unusual.
It is. They use a special forged 4340 steel crankshaft with nitrited journals for strength. And critically, they modify the design so that the hashtag 3 main bearing is specifically beefed up to handle the propeller thrust loads, which is essential for making a car engine reliable in an airplane.
Good overview. Let's quickly mention the certified options sometimes found in LSA because they fit the profile, Continental O200D, Lycoming O233.
Right. The Continental O200D is basically a lightened, updated version of the classic O200. Four cylinders, carbureted, 100 horsepower, weighs around 199 pounds dry. It's a known quantity.
And the Lycoming O233.
That's Lycoming's answer, kind of a modernized O235 derivative. The version often used in LSA is actually experimental, non-certificated, but it's got some nice features, multi-fuel capable, so it can run on unleaded autogas or avgas. Usually has dual electronic CDI ignition, hydraulic lifters like the Jabiru, and it boasts a really high TBO, typically 2,400 hours. So you get proven Lycoming architecture with some modern touches.
Okay, Section 4. This is where the rubber meets the road for you, the AMT student. These are the specific, hands-on procedures you really need to master for LSA work. Let's start with safety, especially around those Rotax engines with their self-generating ignition.
Yeah, safety is paramount, and slightly different here. Because that magneto ignition makes its own power, you can't just rely on turning off the master switch. Before you touch anything, ignition switches OFF, and critically, the ignition system needs to be grounded according to the manual. Usually involves connecting specific pigtail wires to ground.
And disconnect the battery negative terminal, too.
Absolutely, disconnect the battery negative. But the crucial warning is, if those ignition ground wires are not connected, or if they become disconnected while you're working, that ignition is considered live or hot.
That's a scary thought.
Wow.
A prop could potentially kick over just because a grain wire wasn't secure.
It's a very real risk, and fundamentally different from systems that need battery power to make a spark. So if you do need to work on the ignition itself, or have the battery connected for some reason, you absolutely must secure that propeller so it cannot turn, and establish a clear safety zone around it.
Beyond ignition, other best practices. Replacing safety items.
Standard AMT stuff, but maybe even more critical on these lightweight, high-vibration engines. Always use brand new safety wire, new self-locking nuts, new cotter pins whenever you remove them. Don't reuse them.
And marking components before you take things apart. Why is that so important here?
Because these engines often use components made to very tight tolerances, and they wear in together in very specific ways. Things like piston rings in their grooves, bearing shells, gears in the gearbox. Marking them ensures they go back in the exact same position and orientation they came out of. This preserves those established wear patterns and helps maximize the life of the parts.
Okay, let's tackle one of the most common and sometimes tricky tasks on a multi-carb Rotax. Carburetor synchronization. It's a two-stage process, right? Mechanical first, then pneumatic.
Correct. You have to get the mechanical linkage right before you even start the engine. First step is usually to detach the resonator hose between the airbox and carbs, and also the compensating tube that links the float bowls, just to isolate them.
Okay, then the feeler gauge part.
Right. You need a very thin feeler gauge, typically 0.1 millimeter, that's about 4/1000ths of an inch. You place this gauge between the idle speed adjustment screw and the stop on the throttle valve lever itself.
So you find where the screw just touches the stop with the gauge in between.
Exactly. Gently turn the idle screw clockwise until you feel it make contact with the gauge. Then pull the gauge out. Now, turn that same idle screw an additional 1.5 turns clockwise. This sets a precise, small, initial throttle opening.
1.5 turns after contact.
Yes. And you also need to set the idle mixture screw as a baseline, usually about 1.5 turns counterclockwise out from being gently seated. You have to do this identically on both carburetors. The goal is to make sure both throttle butterflies start opening at the exact same time and amount.
That gets the baseline. Then you start the engine for the pneumatic sync.
Right. Now you need sensitive measuring tools, either airflow meters that fit over the carb intakes or precision vacuum gauges like manometer sticks or differential gauges connected to the little ports on the intake manifolds.
What are you looking for?
You're looking for perfectly equal airflow or vacuum readings between the cylinders, initially at idle speed. You make fine adjustments using those same idle speed screws to get them balanced. And here's a caution. Setting the idle speed too low on these geared Rotax engines can actually risk damaging the reduction gearbox.
Too low idle is bad for the gearbox. Why?
Because at very low RPMs, the engine's power pulses can create higher torsional vibrations and harmonics. The gearbox, especially the clutch or damper system inside it, gets hammered by these vibrations much worse than at a smooth, slightly higher idle RPM specified by the manufacturer.
Good to know. What if the readings are way off during the pneumatic check?
If you find you need to adjust one idle screw more than about half a turn to get things balanced, something's likely wrong with the baseline mechanical sync. You should stop, shut down, and go back and repeat the mechanical synchronization carefully. Check the throttle cable adjustments too.
Once idle is balanced, you check the rest of the range.
Yes. Run the engine up towards full power, watching the gauges. They should stay pretty much equal throughout the range. If they diverge as RPM increases, you need to adjust the synchronization for the off-idle range. This usually involves fine-tuning the length of one of the boating cables at the distribution point to make sure both carbs are pulling evenly all the way up.
Okay, carb sync covered. Now that unique oil level check for the dry sump systems, like the Rotax 912 and 914, it's not just pull the dipstick, right?
Absolutely not. This is probably the single most common procedure done incorrectly by people new to Rotax. First, the check should ideally be done when the engine is cool or hasn't run for a bit. The absolute critical step comes before you pull the dipstick.
Which is?
You have to make sure all the oil that has seeped down into the crankcase gets pumped back up into the external oil tank where the dipstick actually measures.
How do you force that oil back up?
You have to manually turn the propeller by hand in the normal direction of rotation. Keep turning it, maybe about 20 full rotations. This spins the engine's oil pumps, specifically the scavenge pump section.
Keep turning
Until you hear a distinct gurgling sound coming from the oil tank. That sound is air being sucked back into the scavenge lines because all the liquid oil has been pushed up into the tank. That gurgle tells you the crankcase is effectively purged of excess oil.
I remember hearing that the first time, thinking something was wrong. But it's the signal it worked. Then you check the dipstick.
Only then. Pull the dipstick, wipe it, reinsert it fully, pull it again, and check the level. You're usually aiming for midway between the minimum and maximum marks. If you check without purging, you'll get a false low reading, add oil, and end up overfilling the system.
Got it. Critical step. What about the oil change procedure itself? Any special cautions there?
Yes, especially regarding the hydraulic valve lifters these engines use. First, the engine should be warm to help the oil drain. You want to change the oil and the filter fairly quickly without long interruptions.
Why quickly?
The key caution is you want to prevent the entire oil system, especially the suction lines from the tank, the oil cooler, and the return lines from draining completely empty. And definitely do not use compressed air to try and blow out the oil lines. Because if you drain the lines completely or blow them out, you can force the oil out of the hydraulic lifters, tappets. Then when you restart, they might be full of air, leading to noise, poor valve operation, or even potential damage until they refill with oil. You want to keep the system essentially primed.
So drain the tank and sump plug, change the filter, refill, and that's it.
Pretty much. And after refilling, it's good practice to, again, turn the engine over by hand, maybe 20 times, just like the oil check purge. This helps refill the filter and all the oil passages, ensuring the lifters and bearings get oil immediately on startup.
Okay. Next up, a really important internal health check for these geared engines, inspecting the magnetic plug.
Yes, the magnetic plug or chip detector. It's usually a special Torx screw plug located strategically on the crankcase, often between cylinder #2 and the gearbox housing. Its job is simple. Attract and hold on to any ferrous metal debris floating in the oil.
So pulling it gives you a window inside the engine and gearbox?
Exactly. You remove it carefully, clean it, and inspect what's stuck to the magnet. You're looking for metal chips or flakes.
What's considered normal wear versus a red flag?
Rotax specifies limits. Generally, a very small amount of fine, hair-like steel fuzz, maybe accumulating to less than 3 millimeters total length if you gathered it all up, is considered normal wear from gears and bearings.
Okay, small fuzz is okay.
But if you find a significant accumulation, larger chips, or any flakes of non-ferrous material, like bronze from bushings or aluminum from the case, that's a red flag. That requires immediate mandatory further inspection. Might involve checking the oil filter, doing a gearbox inspection, or even engine overhaul, depending on what you find.
If it's borderline.
The procedure might call for cleaning the plug, flushing the oil system, putting in a new filter, running the engine for a short period, then pulling the filter and inspecting its contents carefully.
Gotcha. One more specialized Rotax check. The gearbox friction torque check. This only applies to gearboxes with that overload clutch, right?
Correct. This checks the health of the torsional shock absorption unit built into some Rotax gearboxes. It's designed to slip slightly under extreme load, like a prop strike, to protect the crankshaft and propeller.
How do you check its friction?
It's a bit involved. First, you have to lock the crankshaft so it absolutely cannot turn, usually using a special locking pin inserted into the crankcase. With the crank locked, the propeller flange itself is designed to still rotate slightly against the clutch friction, maybe 15 or 30 degrees depending on the gearbox model.
Okay, crank locked, prop can slip a bit. How do you measure the resistance?
You need a calibrated torque wrench, or more commonly, a calibrated spring scale. You attach the scale to a propeller bolt hole at a known distance from the center. Then you carefully pull the scale tangentially, measuring the exact force, in newtons or pounds, required to make the propeller slip smoothly through that small rotational range.
Force times distance gives you the torque.
Exactly. You calculate the friction torque, and there's a specific range it must fall within.
What's the acceptable range?
Typically, it needs to be between a minimum of 25 newton meters, about 18.5 foot-pounds, and a maximum of 60 newton meters, about 44.3 foot-pounds.
What if it's outside that range?
If it's too low, slips too easily, it indicates warm clutch components. If it's too high, hard to slip or won't slip, it indicates binding or damaged components. Either way, if it's outside that specified torque range, the gearbox requires immediate inspection, repair, or overhaul. It's a critical check for gearbox health and driveline protection.
Okay, wrapping up maintenance specifics, let's swing back to the Jabiru engines. They have slightly different recommendations for compression checks, right?
Yeah, Jabiru manuals often mention using just a simple screw-in compression gauge like you'd use on a car. They state that a reading below about 6 bar, or roughly 90 psi, indicates a potential problem.
Simpler, but maybe less informative.
Exactly. They also, and preferably, allow the standard aviation differential pressure test, the leak-down test. That's really the superior method for diagnostics.
And the specifics for a leak-down test on a Jabiru.
Needs to be done with the engine warm or hot. Piston at top dead center on the compression stroke. Standard input pressure is 80 psi. The maximum allowable leakage is 25%. So the gauge reading shouldn't be lower than 80 over 60 psi.
And the key is listening for where the air is escaping.
That's the diagnostic power. Air hissing out the crankcase breather, points to worn piston rings or cylinder bore, air leaking back out the carburetor, bad intake valve seal, air hissing out the exhaust pipe, bad exhaust valve seal tells you exactly where to look.
And finally, that unique Jabiru head bolt torque schedule. That's a recurring item.
It is, and it's critical on these engines due to their direct drive, air-cooled, lightweight construction. Unlike maybe a Lycoming where you torque them and forget them for a long time, Jabiru requires the cylinder head bolts to be checked and retorqued at the first 5 hours of operation, again at 10 hours, and then annually after that.
5, 10, and then annually. What's the torque spec?
They must be torqued cold to 20 foot-pounds. This regular check is vital to maintain the proper head-to-cylinder seal, prevent leaks, and avoid potential head warping on this particular engine design. You can't skip it. #tag outro.
Okay, we've covered a lot of ground. Regulations, 2 strokes, 4 strokes, turbos, maintenance specifics. What's the big takeaway for the AMT student working towards their Powerplant ticket?
I think the main thing is realizing that the LSA world demands precision and strict adherence to the manufacturer's procedures, maybe even more so than with traditional certified engines. These power plants are often a blend of, really specific European designs like Rotax or heavily modified automotive conversions like Aeromax or RevMaster.
So you need the core knowledge, but also mastery of these unique systems and procedures.
Exactly. You need to master that Rotax dry sump oil check, the nuances of multi-carb sync, maybe a gearbox friction check, right alongside your understanding of basic engine principles. It's specialized.
But the reward is getting to work on these really cutting-edge, high-power-to-weight engines that are honestly shaping the future of personal flight.
Absolutely. And that brings us maybe to a final thought, kind of tying back to safety and diagnostics. We talked earlier about how severe overheating in some engines can cause run-on or dieseling, where the engine keeps sputtering even after you switch the ignition off.
Right, that's a clear sign of major thermal distress. Time to land, ASAP.
Definitely a sign something's gone very wrong. But the real challenge for you as a future AMT is catching problems before they get that bad. Think about something a pilot might report, maybe a sudden, sustained increase in oil consumption that wasn't there before, or maybe an unusual vibration that just started appearing in cruise flight.
Seems minor, maybe.
Could seem minor. But what other subtle observation, what other piece of operational feedback from the pilot might be the very first clue of a slow-motion failure brewing deep inside? Maybe in the turbo bearings, or the reduction gearbox dogs, or even the engine structure itself. The best AMTs don't just fix what's obviously broken, they use those subtle clues, that operational feedback, to anticipate failures before they become catastrophic. That's the level of critical thinking, that diagnostic intuition you should be striving for.